It's kind of cheesy.
The recording is in progress. Let's rock and roll. This is the last lecture. I'm not going to die, despite what some of you may wish of me right now. It's just the last thing I have to tell you about OCHEM 1. Some of you may continue on with me with OCHEM 2, but otherwise we will call this good. The last thing we need to talk about is our last spectroscopic technique called NMR. So typically when I give this talk, I'll have a few slides here at the beginning about what an NMR is, how it works, but we're going to jump straight to how to read an NMR because we are, as you have noticed, a bit pressed for time. And the main thing I want is for you to be able to deconvolute, to be given a spectrum and a formula, and tell me what the full chemical structure is. As I have been mentioning for the last several days, NMR is, I think, the hardest spectroscopic technique we do, but it's also the most informative. If you brought me an unknown molecule and said, I need to know what this is, but you can only do one thing to look at it, far and away, I would use a proton NMR. Every organic chemist would use a proton NMR. If I could get a good, clean proton NMR, I can tell you the exact structure. As we've seen with IR, I can only tell you functional groups. With mass spec, I can only tell you the molecular formula, but it's really hard to tell the exact structure. I can tell you pieces of it, but the exact structure is difficult. Proton NMR is not that way. I can tell you exactly where most things are included in a proton NMR just from that one spectrum. NMR stands for nuclear magnetic resonance. You may be familiar with a technique that sprang from this. So this was developed to look at organic molecules, but then we realized, well, we're looking at protons. Protons are also attached to water, so you can actually map out where water is. And if you do that in the human body, that is called magnetic resonance imaging, or MRI. Hopefully, you've not had too many MRIs in your life because that means something has gone not right. But if you have had an MRI or you're familiar with MRIs, you know that it is the yin to the X-ray yang. So if I take an X-ray in my body, I'll see all the hard stuff, all the bones, my thick skull, I'll see that stuff. If I take an MRI of my body, I'll see all the squishy parts. Well, I'm pretty squishy all over, right? So my brain matter, all my fat, all the cartilage in my body, those things can be seen with MRI. So if you've had a soft tissue injury, you look at it with MRI. If you have a bone break, you look at it with X-ray. MRI and NMRs work the same way. You put the sample into a giant magnet that causes all the protons to line up. So if you've seen, or if you've ever been in an MRI machine, or you've seen someone go into an MRI machine, you know, it's the big donut. The big donut is actually just a really strong magnet. The whole purpose of that is to get all the water molecules to face the same way in your body. Once they do, you hit it with a radio frequency and you look at what the protons do when they interact with that radio frequency. That is your very short primer on how MRIs and NMRs work. We're going to get 3 pieces of information from the NMR. I'm going to talk about them in order of chemical shift, integration, and splitting. But we're going to use all 3 of these to come up with the structure for a molecule. And one of the things I'm going to encourage you to do is when you see an NMR, I don't want you to look at the NMR like a painting and then tell me what you see. I want you to pick it apart into these individual pieces. Tell me what the chemical shift tells you. Tell me what the integration tells you. Tell me what the splitting tells you. Make little pieces of the molecule and then put it back together. The 3 pieces, chemical shift is the electronic environment. There's something about the number of electrons that are around a proton that are going to influence this. Integration is the number of protons in a particular area. So is it a CH3 or is it a CH2? And then the splitting pattern, that's going to tell you something about how many protons are near each other. So we'll go through these one at a time. One last thing that I want to mention here is notice that when I say proton NMR, I wrote a 1 with an H over here. That's referring to a particular isotope of hydrogen, protium, right, which has no neutrons, just 1 proton in it. This is what we call spin active. These molecules, this type of nucleus, responds to a magnetic field. You have to have an odd number up here for it to respond to a magnetic field. Most of carbon in the universe is carbon-12. That's what we call NMR silent. When I put carbon-12 into an NMR, it doesn't register at all. Carbon-13 does. And for that reason, we can take a carbon NMR, but only of carbon-13. Problem there is carbon-13 represents such a small fraction of carbon in the universe that it's not very helpful. So there are a great number of NMRs out there. Proton NMR is the one we'll focus on. I'm going to show you a carbon NMR, and that's about it. But proton NMR is the most information dense because it is a spectroscopically active nucleus. Let's start with the chemical shift down here. So this is what an NMR typically looks like. It's read in parts per million. We'll come back to that in a little bit. 0 to 10, it actually goes up to 12, 13, 14 as well. On the right-hand side, that is what we call a highly shielded environment. And on the left-hand side, we call that a de-shielded environment. What I mean by shielding is, I mentioned that the instrument works by a radio frequency. So you have your proton sitting here, you hit it with a radio frequency, and the proton responds to that radio frequency. If there's a lot of electron density around the outside, that kind of acts like earmuffs for the protons. So over here, I've got protons with earmuffs on, and I'm going, hey, protons. And they go, mm-mm. And I go, hey, protons. And they're like, mm-mm. And I have to just get louder and louder and louder until they hear me. It's like turning the volume up on our radio frequency. We call that upfield or high field or shielded. So if you're on the right-hand side of a spectrum, you are shielded, or we call that upfield, increasing the volume on the radio. On the other side over here, you're a proton attached to something that is stealing electron density from it. So I can say, hey, proton, and it'll hear me, and I don't have to turn the volume up on my radio. We call that downfield or de-shielded. So the x-axis here is going to tell us about the electronic environment where a proton is in the molecule. We use an internal standard. This thing is called tetramethylsilane. The reason for that is, if you look where silica is on the periodic table, it is directly underneath carbon. So it is equivalent to carbon, but it's less electronegative. So all these CH3s that are attached to the silicon are very electron rich, because the silicon is sharing electron density with the carbons. Pretty much nothing else is more shielded than TMS. So we set that as a 0 point, and everything is measured as a chemical shift away from TMS. The reason we do that is that if I run an NMR in Broken Arrow and you run an NMR in Tahlequah on a different machine, we need our numbers to be the same. And so we don't want them to just be how strong was your magnet, how concentrated was the sample. We want to compare it to a standard, and TMS is the standard for each one of these things. This is approximately where you would find protons. I don't want you don't have to necessarily memorize these numbers, but I think it's helpful for a trend to see what I mean by shielded versus de-shielded. So on the right-hand side over here, this is an alkane, a saturated molecule. Nothing is stealing electron density from this molecule. And so the protons are relatively saturated or relatively coated in electron density. Meaning if I want that proton to hear my radio frequency, I have to turn the radio up. The volume, literally I have to turn the volume on my radio frequency higher. We call it the amplitude. Over here, I have added an electronegative atom to that carbon. So an oxygen or a nitrogen steals electron density from this carbon, which then steals electron density from that hydrogen. So I would say this hydrogen is de-shielded because of that oxygen and nitrogen compared to that hydrogen. For that reason, this hydrogen is going to show up somewhere to the left, downfield, de-shielded to where this proton would show up. Those words you're going to hear me use, I would say this proton is downfield of this proton. It is in a less shielded environment, so I don't have to have my radio frequency as loud. That carbon's sp3 hybridized, that carbon's sp3 hybridized, that carbon's sp3 hybridized. All the carbons have the same hybridization. They're all sharing equally. It's what's happening outside of the carbon that's influencing it. Look what happens when I go to an sp2 hybridized carbon. Even worse, because the hydrogen's bound to something, the carbon itself is more electronegative than these carbons. So we would see protons that are bound to double bonds show up in about this region. Benzene is special. I've alluded to that before, but you don't need to know why, but benzene really steals a lot of electron density into the middle of the ring. So if you're a proton on what's called an aromatic ring, you show up further down here. There are protons that show up even farther this way, even further downfield. And we'll cover those a little bit later on, but this is a general layout of what I mean of I have a lot of electron density, I am upfield, or I have very little electron density, I am downfield. This would show up as a peak over here. This would show up as a peak over here. The x-axis is going to tell us something about how many electrons are in the system. Don't worry about that. Here is an example of a molecule called methyl acetate. So this is the full structure of the molecule. The way I'm going to give these to you as a problem is I will give you the molecular formula and I will have you draw this. This is going to be the answer. So what I would say is given this spectrum, draw a molecule that has a formula C123 H6O2. One of the first things you should do when given this formula is calculate your degrees of unsaturation. Since you can see it down here, how many degrees of unsaturation does this molecule have? 1. It's a carbon-oxygen double bond. Now you wouldn't know that. You would just calculate it and say, okay, this has 1 degree of unsaturation. The next thing you're going to do is you're going to go over here and look at your chemical shift. I have 2 peaks here, and hopefully they show up for you the same color here, kind of red and green. Yeah. Is this showing up well enough in here? Then you turn off more lights that those protons are green and those protons are red. You see that? And if I turn off one more set of lights, you're going to fall asleep on me. I'll try and make it extra exciting. Any better? Okay. I think for the Zoom folks, now it's getting really dark. And I look like I'm telling ghost stories now. You guys can see. And then next, the proton, just when you thought you were safe. Okay, so I have 2 peaks here. There's a peak in green on the right. There's a peak in red on the left. Which one of these peaks, green or red, is de-shielded? Which one has less electron density around it? The one in red. So what I would anticipate is whatever's going on with those protons, they are attached to something that's stealing electron density. What in my formula could be stealing electron density? The oxygen. So I'm thinking the protons in this signal are probably nearby an oxygen, and the protons in this signal are maybe a little bit further away from an oxygen because oxygen's electronegative, so it steals electron density. Well, look down here. The protons in green are on a carbon attached to a carbon that has oxygens on it. The protons in red are on a carbon directly attached to an oxygen. So the protons in red are less shielded. They are de-shielded. They are downfield of the protons in green. One signal here, one signal there. Now notice that there's 3 protons here, but I only drew 1 spike. There's 3 protons here, but there's only 1 spike. NMR is a relatively slow technique. It measures over seconds. These 3 protons are spinning around on the femtosecond time scale. So in the time that it takes me to snap, that molecule has rotated about 11 billion times. Very, very fast. So as far as my NMR is concerned, it looks down there and goes, whoa, guys, there's 3 protons, but they're going crazy. It can't distinguish any of these. They're triplets, identical triplets. Right? So 1 peak for the signal in red, 1 peak for the signal in green. The signal in green is more electron rich because it's further from the oxygens. The signal in red is less electron rich because it's closer to the oxygens. That part makes sense so far? Yeah.
Like you need this stuff in the CMR, like branching 1450 that apply here now.
The carbon NMR would just show you 3 different signals for the carbons. Let's put a pin in that though. I'll come back to carbon NMR. Yeah.
Is it always going to be for hydrogen?
It's always going to be for hydrogens. A proton NMR is always hydrogens. So I think that's what makes NMR more challenging. My instrument can see the 3 protons in red, and it can see the 3 protons in green. It cannot see the carbon, that carbon, that carbon, that oxygen, or that oxygen. I'm going to have to mentally supply all of that. That's where the hard part comes in. Now, I'm going to give you a formula to do this, but you're going to look at, this is a little esoteric, but has anybody read or heard about the analogy of the cave? Not analogy, allegory of the cave. It's a thing from, I think it's Plato. So Plato had this philosophy of human beings are kind of like, he had this story where, how much do I want to go into this? Maybe this will be helpful. There's a story where there's these people that were born into a cave chained to a wall. All they can see are shadows being cast on the wall in front of them. So there's a fire out back behind them, and there's people out in the world running back and forth in front of the fire. So all I've ever seen in my entire life is just a shadow cast on the wall. So I assume that the world is just the shadow on the wall. Well, eventually these people get out of the cave and they realize, wait, that's not the world. We're just seeing shadows of what the world actually is. And that is the basis for human discovery in Plato's mind. It's called the allegory of the cave. I think of that with these NMR signals. All I see are these two peaks. I have to fill in the rest of this because these two peaks mean more than just the protons that are here and here. There are other things that allow the protons to interact together. So what we're going to do is use the three pieces of information from an NMR and take the shadows of the protons to fill in the full molecule. So we'll get to that here in a second, but sorry, that's probably not super helpful unless you are steeped in Plato, in which case you should check out Plato. It's pretty cool. That is chemical shift. That is the x-axis here. Things that are electron poor are on the right. Things that are, things that are electron rich are on the right. Things that are electron poor are on the left. Now, this NMR is pretty simple because the signal in green and the signal in red are the same height. Let's look at what if there are not the same number of protons. So 3 protons over here, 3 protons over here. There's a 1-to-1 relationship. What if there's not? Here's a very similar molecule, except now I have a CH3, CH3, CH3 that are all identical, and a CH3 over here that is different. Now I have a 1-to-3 relationship. Well, look what happened to my signals. My signal in red is shorter, and my signal in green is taller. That is called the integration. Integration is calculus for area under the curve. That is, the height of this peak is indicative of how many protons are in that peak. The molecular formula for this molecule would be 1, 2, 3, 4, 5, 6 carbons, 9, 10, 11, 12 hydrogens, O2. So you'd be given this, I would have you give me the full structure based on that molecular formula. You would go through here and figure out that this molecule has 1 degree of unsaturation. And then you would go to work over here, starting to look at the factors we've talked about. The first thing I think you should do is figure out how many different signals do I have? I have 1 here and I have 1 there. So I have 2 different populations of protons that are in here. Which population of protons, the green, I can't see my keyboard, the green or the red is less shielded, is de-shielded, green or red? Red. So I'm thinking these protons are probably closer to the oxygens in this molecule. Helpful things to first think about. Next thing I want to do is try and figure out how many protons are present in each one of these signals. There are 3 different ways that you'll see integration shown in an NMR. The most common is a box over here. So what you're going to see is a list of the chemical shift and its relative area. You'll also see these little funny lines. And if someone's being really nice to you, and occasionally I am really nice, you'll see numbers defined above the peak. Let's go through each one of those one at a time. The most common one is this box over here with the chemical shift and the relative area. At a chemical shift of 1.2, that's this signal, there is a relative area of 3 protons. At a chemical shift of 3.65, there is a relative area of 1 proton. Here's the problem. I need to account for 12 protons. And you might have noticed that 1 plus 3 equals 4. Not really good at math, but 4 is not 12. If you're smart, you'll look at that and say, well, 4 could be 12 if I multiplied it by 3. This is the relative area. So these numbers can be multiplied to get to your final count. Real talk, and I tell on myself all the time, but here's how bad I am at math. I don't typically do it this way, where I add these up and figure out what multiple this is of the final number. I guess and check, because that's just how my simple little mind works. So I'd go over here and say 3 plus 1 is 4, 4 is not 12. So let me multiply them. I'm going to start by multiplying them by 2, because I'm not very smart. 2 times 3 is 6. 2 times 1 is 2. 6 plus 2 is 8. 8 is still not 12. So I better go back and multiply these again. 3 times 3 is 9. 3 times 1 is 3. 9 and 3 is 12. Now I'm done. So what I'm going to do is take these numbers and say my chemical shift of 1.2, this one, is worth 9H. When you see someone write a number, an H, above a peak, that means it is defined by that number. I don't multiply or divide anything here. There are 9 protons represented in this peak. This signal at 3.65 here is worth 3 protons. Defined as 3 protons. Questions so far?
Couldn't you just, like, look at the flow of the map, and just be like, the total's 12. This like little peak added up 3 times, 53. Let's keep it.
So Gunner's asking about the final thing here. Could I also not just take this peak and figure out how many times this peak will fit into that peak? Yes, you can. And I think this is actually the most, the way you propose is not annoying. The thing I'm going to show you is, I think, the most annoying way of doing this. Back in the day, when I was first learning NMR, computers were not as good as what they are now. It's actually really hard to do integration. There's a lot of math involved in this. So before we started getting relative areas that were defined like this, we would get these lines. These are called integration lines. An integration line can be viewed as, where does the line enter the signal and where does it leave the signal? You're going to take that as a unit. You find your smallest unit, which would be this one, and you figure out how many times can I get that to fit into my other signal. So there's my unit. How many times can I get that to fit in over here? Well, by my crappy drawing, it looks like about 3 times, right? So a 1 to 3 relationship is shown by these stair steps. Those integration lines, I think, are the most challenging because you have to it's a judgment call about how well they fit in there. But they're actually better than how my professors learned this. So the people who taught me NMR computers were even worse back then, right? So they had this thing called integration paper. And what they would do is print off their NMR, and then they had a special place where they put on white cotton gloves, and they had very special scissors. They would cut out the peaks of the NMR. They would take them over to an analytical balance, and they would weigh them. So the way that it would work would be like, here's my spectrum. I would go and cut very carefully out this signal. So I'd have a sliver of paper that big, and then I'd cut out this signal of paper, or this sample. And I would go and weigh this. And based on the relative weights of those 2 things, that's how I would get the integration. So it was like, how good is your arts and crafts would determine how well you determine the structure. So we've gotten a lot better since then. But those are I can't erase all this. Those are the 3 different ways you're going to see integration. Most commonly, you're going to see a box over here. The relative area can be multiplied. If I multiply one number, I have to multiply all the numbers by the same number. You'll also see maybe these lines. Those are a little bit open to interpretation as well. How well do these things fit into each other? And then you'll also see these things with 3H or 9H defined above the peak. If you see 9H here, you don't multiply it. There are 9 protons in that signal. And again, those 9 protons are represented here, 3, 6, 9. My NMR thinks that all these CH3s are the exact same because chemically they're in the same environment and they're spinning around so much that it just says, it'd be like when I walk into my son's daycare, be like, there's like a dozen kids in here. I don't know who they are. It's just chaos, but I can figure out there's about like 12 kids in here just moving about like crazy. They all look the same to me. Little ankle biters all over the place. Questions about integration? Folks online, you can contribute here as well. We're doing okay? Yeah. Did everybody read chapter 13 in advance? And so that's why we're all doing okay. Who has good ideas? Sometimes. Sometimes. Here's another example of another type of integration. So this molecule is called acetamide. Again, its molecular formula. This would be the answer. So its molecular formula is C2H4O. You could do your degrees of unsaturation there and find out this has 1 degree of unsaturation. We'll come back to that. So I don't just keep writing that down for you. Based on our formula or on our spectrum over here, I have a signal over here and a signal over here. These guys that are next to it are just blow-ups of those signals. We'll come back to that. That's our final topic called splitting. So put a pin in that. But I have 2 different signals that are in here. Which one of these signals, the green or the red, is more electron rich? The green. So whatever protons are over here, they are probably farther away from the oxygen than the protons in red. So I have a signal that's relatively shielded, and I have a signal that's very de-shielded, right? Look how far out we are, 10. We're going to find out that things that show up at 10 are either aldehydes or carboxylic acids. That's the only two signals that go that far out, but this is a very de-shielded proton. Next thing I want to do is make sure, do my integrations match the total number of protons I'm looking for here? I need to account for 4 protons in my unknown formula. How many protons have I been given? 4. I don't need to multiply these numbers at all. They're good to go. So the signal at 2.23, that's this guy, is worth 3 protons. The signal at 9.79, that's this guy, is worth 1 proton. Those are my integrations. I have 1 proton that is very de-shielded. I have 3 protons that are relatively shielded. Okay. The last thing that we need to talk about is what's going on with all this. Why do those look crazy like that? There is a thing in NMR called splitting. The number of protons that are neighboring another proton influence what the signal looks like. So this tells you about kind of the environment. If you are sitting, so right now I'm in the, you guys that are online, you know this, I'm up here at the podium kind of by myself. If we took an NMR of this room, I would show up as a signal that has no splitting pattern because I don't have anybody around me. But if I took an NMR of everybody sitting in the classroom, you have people around you. So your signal is going to start to get more complicated because you have neighbors that are influencing your signal pattern. Bless you, the splitting is also a way of talking about the number of neighboring protons. So I think this is probably the hardest part of this and can be, depending on the type of the spectrum you have, can be helpful, or sometimes the splitting pattern isn't going to be useful to you at all. For those of you taking the lab, I hear you had a very fun time with NMR. Sarah and I had a powwow yesterday, and she was like, hey, so apparently I did NMR before you, and everyone was really confused. And I was like, that probably makes sense. If you take the lab, she gave you real world NMR data. And so for many of you, you probably realized, 1, I don't know what this is. And 2, if you look at it again, the splitting patterns are worthless. It's just like, you can't get anything out of it. It's just fuzz, right? So you don't always get a splitting pattern. Here's how we do splitting. We are going to look at the number of peaks, or what we call a multiplet, based on the n+1 rule. If a proton has no neighbors, n equals 0. So its signal is going to look like 1 peak. If a proton has 1 neighbor, n equals 1, 1 + 1 is 2, it's going to be represented by 2 peaks. If a proton has 2 neighbors, 2 + 1 is 3, it'll have 3 peaks. This is a 3-peaked signal. We call that a triplet. 1, 2, 3. If a proton has 3 neighbors, 3 + 1 is 4. That makes a multiplet we call a quartet. That's this guy. 1, 2, 3, 4. Now, some things that I want us to be familiar with. I'm going to show you some really ugly splitting patterns because this is laid out really nicely, but I need you to be able to tell this is a quartet from this monstrosity. And same thing here. I need you to be able to look at this signal and tell me that it's a triplet, because you won't always see these things really nicely delineated and nice and clean. Where do these come from? Actually, first off, let's go through, and before we get to the splitting pattern here, let's recount what we're doing here. C2H5Br. I'm just turning that molecule into this formula. I need to account for 5 hydrogens. Do I have 5 hydrogens over here? No, I have 2.5 hydrogens. I must multiply these numbers. So what I'm going to do is multiply this by 2 and that by 2. 1.5 times 2 is 3. 1 times 2 is 2. 3 + 2 is 5. So I'm going to take those integrations and say that this signal is worth 3 protons and that signal is worth 2 protons. Which signal, the blue or the red, is less electron rich? The red signal is less electron rich. What in my formula could be stealing electron density? The bromine is my electronegative atom. So I'm thinking the signal in red is probably closer to the bromine than the signal in blue. because the bromine's still in electron density, that's. This is the structure. The neighborhood. The carbon are the house. So have neighbors on either side. Out in the country, imagine you live in a suburban neighborhood. I don't know.
Oh, there you are.
I'm back. I have no idea what just happened. I decided that we don't want to talk anymore, but the recording's still going, so that face just got recorded forever. That's great. Let's put this back. Okay. Splitting. So I think Zoom was like, dude, shut up. This is horrible. You're gonna like no more. The carbons in a molecule are like houses on the street. The protons are people who live in those houses. Not every house has the same number of people. So in this neighborhood, I have two houses, the blue house and the red house. The blue house has 3 people that live in it. The red house has 2 people that live in it. So when I talk about how many neighbors do you have, it's not how many houses are nearby, it's literally how many neighbors are there. The blue house has 2 neighbors because the house next door has 2 people that live in it. The red house has 3 neighbors because the house next door has 3 people that lives in it. Thus, the blue signal having 2 neighbors means that the blue signal splits 2 plus 1 or into a triplet. My blue signal has 1, 2, 3 peaks. The red house has 3 neighbors, meaning 3 plus 1. My red signal is going to show up as a quartet, 1, 2, 3, 4 peaks. That's how we're going to use this splitting pattern to tell you about how many neighboring protons are there to the signal you're looking at. We're going to go through this a little bit more, so before I really pause for questions here. Sorry to the mathematicians in the audience. Pascal's triangle is why this is the case, but don't worry about it. They split. Just take my word for it. Here's the thing. I searched the internet for the ugliest possible splitting patterns I could find, because I need you to be able to tell splitting patterns even when they're not laid out very nicely. This is a singlet, even though it looks like there's some other stuff going on here. This is a doublet, even though there's like a lot of things going on here. The way that I'm going to have you memorize this is the overall symmetry of the signal. A singlet generally gets taller and taller and taller as it moves up. I like to think of these kind of like buildings. Has anybody seen the Burj Khalifa or been to Dubai? The Burj, sorry, maybe the name's not familiar to you. You've probably seen it. We were talking about Mission Impossible in here earlier. The Burj Khalifa is this ridiculously tall building in Dubai. You have seen a picture of it at some point because Dubai is a big city and they've got some tall buildings, but there's this building that's like 10 times as tall as everything else. The Burj Khalifa, to me, looks like a singlet. There's like structure to it. There's little balconies and terraces along the way, but it gets taller and skinnier along the way until it gets to the top. And then for some reason, Tom Cruise breaks out a window and runs down it. He actually did that, crazy person. A singlet does the same thing. It's okay that there's stuff going on down here, but it's just getting taller and skinnier as we go up here. A doublet is 2 equally tall peaks. So that would be like the Twin Towers when they were still standing, right? So there can be structure to them, but you have 2 signals that show up roughly the same height. A triplet, I think, kind of looks like a psi. If you're into Teenage Mutant Ninja Turtles, that would be a short peak, tall peak, short peak. And again, there's some structure in each one of these, but you see the short, tall, short. A quartet is a short, tall, tall, short. Anything beyond a singlet, doublet, triplet, or quartet, anything more than a quartet, we're going to just call a multiplet. I do not want you to try and count any more than 4 peaks. If you count more than 4, you just say there's a lot of neighbors. Because they're showing in heptet here, but you have to have an incredibly strong magnet to be able to see that. I want you to just say there's a lot of neighbors. I don't know how many, but it's surrounded by a lot of protons. Let me move some of these things off of here. Can everybody see without my marks? Let me get rid of this. And everybody tell that this is 1 peak. And that's 2 peaks. And this is 3 peaks, short, tall, short. This is 4 peaks, short, tall, tall, short. Again, I know this graphic looks bad. It's also kind of fuzzy. I intentionally found something like this because this looks more like real world data. That is more real than something you're going to see that looks like this. This is artificial. It's cleaned up for you to look this way. Most data is going to look, pretend like you can't see this. I need you to make a determination on that line alone. And it can be tough. There's a short line here. There's the top of the tall line. There's the short line over here. There's a short line here, tall, tall, short. For those of you in the room with me right now, it's probably even harder to see. For those of you online, it's probably a little bit easier because it's crisper. If you saw this printed though, you'd be able to see this. So for you guys in the room with me now, watch the recording and see if, or look at the PowerPoint, and that's maybe a easier way to see this. When it's printed, I will make sure you can see it well enough, but it's not always going to be nice and blown up. Okay. I'm going to, another way of me saying this is, I'm going to endeavor to give you real world NMR data, not always just a sterilized cartoon depiction of data. I mentioned previously that carbon NMR is a thing. This is my only time for bringing it up. Carbon-13 is NMR active. Carbon-13 represents only 1% of carbon in the universe. 99% of carbon in the universe does not show up on an NMR, which means I cannot get integration and I can't get splitting information because it's very unlikely in a molecule that has 6 carbons in a row that you would ever have 2 carbons next to each other that are both carbon-13s. Statistically, that's just improbable. 99% chance they're all carbon-12. So here is a proton NMR of this molecule, methyl acetate. And here's a carbon NMR of methyl acetate. Some things they have in common. They both are presented in chemical shift, but notice the scale is different, 0 to 200 for the carbon and 0 to 10 for the proton. Everybody is a singlet in a carbon NMR. There is no splitting. There are no integrations to be gotten from this either. So I can't tell you how many carbons are here. I can't tell you how many carbons are here. I can't tell you how many carbons are here. The only thing I can tell you is there are 3 different carbons and that this carbon is the most de-shielded. So that applies to the carbon that has all the oxygen on it is the most de-shielded. The carbon that's attached to an oxygen is a little bit less shielded than the carbon that is attached to another carbon. I can't tell you much about the product from this carbon NMR. If I knew the molecular formula and just this proton NMR, I can tell you this entire structure. So that's what we're going to endeavor to do is I'm going to give you a molecular formula and just the proton NMR, and you're going to build the rest of this in. So we don't talk about carbon NMR more than this because it's extremely limited in what you can get from it. Carbon NMR tells you only chemical shift. Okay. What I'm going to do is work through this one, and then I'm going to unleash us on a couple problems that I want you to try on your own. When I do that, I want you to actually try this. If you just sit and watch me work these problems, you're missing out on an opportunity to work this in real time and ask me questions. So I'm going to spend about 15-ish minutes working this problem because this is how it's going to be presented to you. And then we're going to try and do at least 1, hopefully 2 examples where you work the problems and then we all solve them together. Okay. So this is how you'll see it on the exam. I'm going to ask you at least 1, maybe 2 questions about these type of techniques on the final. Propose a structure for a molecule with the chemical formula C4H10O from the proton NMR spectra shown below. It should be spectrum, typo. There's only 1 spectrum here, right? Spectra is multiple. First thing I want to do is figure out if I have any degrees of unsaturation. So remember when I brought this up with alkenes, I said we will use this again at the end of class. we have arrived. The degrees of unsaturation is going to help me determine, do I have any rings or double bonds present? Because I need to build this molecule, so I need that information. Are there any pi bonds? Are there any rings? There are not, right? So the way I would calculate that is my formula is C4H10, ignoring the oxygen. A saturated molecule would have C4, 4 times 2 is 8, plus 2 is 10. I'm missing 0 hydrogens, so I have 0 degrees of unsaturation. I have no rings, I have no double bonds present in this molecule. That is helpful to know from the outset before I try and build it. The next thing I'm going to do is see if my relative area adds up to the total number of protons. I need to account for 10 protons. Do I have 10 protons down here? No. So I got to multiply. If you are smarter than I am, you add these together and say that's 2.5. 2.5 needs to be multiplied by what to get to 10? 4. Or you do what I do and you go, 2.5 is not 10. How to make 2.5 10? I'm going to start with multiplying them by 2. 1.5 times 2 is 3. 1 times 2 is 2. 3 plus 2 is 5. 5 is not 10. So I better multiply by the next number. Now I am smart enough to know that 5 is half of 10. So I'm going to skip over multiplying these by 3, and I'm going to say, let's multiply these by 4. 1.5 times 4 is 6 protons. 1 times 4 is 4 protons, which means 10 protons total. My signal at 1.2, that's this guy, is worth 6 protons. My signal at 3.49, that's this guy, is worth 4 protons. See how I did that? Okay. Here's a challenge. I'm putting hydrogens onto carbons. In a chain, how many hydrogens can I possibly put on one carbon? 3. The answer is not 4 because 4 would be methane. This molecule is very clearly not methane. So if it's anything larger than methane, the maximum number of protons a carbon can hold is 3. Well, if you see an integration higher than 3, it means you have to have multiple carbons that are in the same chemical environment. Well, look at my signals, 6H here and 4H there. Both my signals are higher than 3. So what I'm thinking is going on here is I've got a symmetric molecule. One half of this molecule mirrors the other half of the molecule because I've got to split these in half. So what I'm going to do is solve this as 2 signals of 3 hydrogens. I'm going to solve this as 2 signals of 2 hydrogens. And that'll make more sense here in a little bit. The way I'm going to approach this is if I have 3 protons on a carbon, I'm going to say it's a CH3. That CH3 is bound to a carbon that has how many protons on it? How many neighbors does this CH3 have? 2. How do you know that, Caleb? There's 3 peaks, which is a triplet. This signal is a triplet, which means my CH3 must be next to a CH2. I drew all of that, a CH3, CH2 bound as something. I'm just leaving it generic from this one peak alone. Now I had to assume a lot of things there, right? I was given a 6H. I assumed I'm working with 3 H's instead, because I'm going to split this in half. And then I used the splitting pattern to tell me about the CH2 that's nearby. This is going to take some practice. This is, I think, why it's so hard. That I just drew a whole bunch of stuff from one signal. Let's try it over here. Instead of it being 4H, I think that I'm having 2 CH2s that are equivalent to each other. So I'm going to draw a CH2 that has how many neighbors? Really? 3. Why do you say that? There's 4 peaks here, right? So 4 peaks means n plus 1, or in this case, n minus 1. 4 peaks means I have a CH3 nearby. My CH2 would have 3 neighbors, so my CH2 would show up as a quartet. I don't know what else this is bound to, but that exists somewhere in the molecule. Well, look what I just did. I drew a CH2 next to a CH3. Over here, I drew a CH3 next to a CH2. what are the chances that those two pieces are related to each other? Pretty good. So what I'm doing is I'm building up puzzle pieces here and saying this part of the molecule probably looks like this, and this part of the molecule probably looks like this, but just like a puzzle piece, maybe I've got a peg and a slot that fit into each other here. So a CH3 and a CH2 could be, maybe that's the CH2 of it here, and that's the CH3 of it here. Which one of these signals, my CH3 or my CH2, is more de-shielded? The CH2 is more de-shielded because it shows up farther to the left, further downfield. So what is likely here? What's likely here? In oxygen, I have an electronegative atom that I can use to pull that away. So I didn't define this, but it's very likely that I have a CH3 next to a CH2 next to an oxygen, because that means that this CH2 would be de-shielded compared to the CH3. The CH2 would show up further to the left. Well, I've accounted for 1, 2 of my 4 carbons, 3, 4, 5 of my hydrogens, and my oxygen. What goes over here? CH2, CH3. Remember when I started this, I said, well, I got 6 and 4, that doesn't work. So I'm going to solve this as maybe 2 CH3s and 2 CH2s. Here's the symmetry in the molecule. The CH3 and the CH2 can go over here so that these guys are the same. They would show up as one signal because the CH3s are chemically equivalent as far as my NMR is concerned. And these guys are the same. My CH2s would show up as the same signal. I would only have 2 signals in this molecule, even though it's more complicated than that. The last thing I want to do is, this is the structure I'm proposing. So when you do this, I want to see notes all over your NMR. Do not just draw a structure on here. This is the part where I'm trying to encourage you to not look like an NMR, not look at an NMR like a painting. If you're into fine art, that's great. You walk up to a fine art piece and you stare at it for a while and you're like, I see the future. And then maybe somebody else walks up and they're like, what are you talking about? It's a cow in a field. The future, you look, and flies maybe, right? Don't look at an NMR like a painting. If you just look at it and then say, ooh, I see this molecule, you will convince yourself that's the molecule. You will draw crazy things and you'll spend forever trying to make your molecule fit the spectrum. That's probably not correct. Instead, what I want you to do is look at an NMR like puzzle pieces. Draw the puzzle piece. That's one. That's the other one. Then start putting the puzzle pieces together to draw the final thing. Show me your work. If you draw for me only the thing that's in the box and it's wrong, it's very hard for me to give you partial credit. If you draw everything I have on the screen right now and you get what's wrong, you get the box wrong, I can give you way more than even half partial credit because you showed me, you know how to do degrees of saturation. You know what integration's about. You know what splitting's about. So show your work when you're working through these things. You can get a lot of points from just attempting it, even if you don't get the final answer here. The last thing I'm going to do to double check myself is I'm going to figure out what would an NMR of my molecule in the box look like. I've got too many circles on here, just the box. I have a CH3. Maybe I can put them in some colors here. Why is it in green? We'll use the space pen. I've got a CH3 over here and a CH3 over here in my fabulous pen. Those two CH3s are chemically equivalent. That should show up farthest to the right because that signal is the most shielded. It would integrate to 6 and it would look like a triplet because the CH3 only has 2 neighbors. Well, I have a signal over here that integrates to 6 and shows up as a triplet. Yay. I would expect another signal. Those CH2s are equivalent. That adds up to 4 because the CH2 here and the CH2 here are chemically equivalent. So I'm looking for an integration of 4. That integration should be de-shielded or to the left of my other signal. And because the CH2s each have 3 neighbors, that would be a quartet. So I'm looking for a quartet to the left of my other signal that integrates to 4. There. I'm feeling pretty good that that's the molecule. We see the task at hand. Yeah.
So like, you would like
I think the order is find degrees of unsaturation. Make sure that your integration makes sense. So make sure your integration adds up to the protons you're looking for. Then go through and start trying to build puzzle pieces. Then put the puzzle pieces together. 1, 2, 3, learn by doing. I'm gonna turn the lights on. Let's get after it. I'll turn one on. And just a heads up to our Zoom folks. I will be bugging you at some point, so. Be ready to contribute if you would please. How we doing, Zoom folks? Just peruse the classroom over here. There's some thoughts. Emily, one, or Charisse, can I have one of you tell me about the degrees of unsaturation for this molecule? It's super straightforward. You just push your space bar and it'll unmute you and you're good to go. Charisse has a thought. Maybe push and hold, sorry, click, Sharice, click on the Zoom window and then push and hold your space bar. It's like a walkie-talkie. There you go.
0. I got 0.
0, very good. So you added the bromine to your hydrogen count, which gives you a formula of C4H10. C4H10 is a fully saturated molecule. What's that tell you, Sharice?
I don't know.
It tells you
I got lost after that.
0, it just tells you nothing. It tells you that you have no double bonds or rings present in that molecule. You're going to have only single bonds present. Because if you put a double bond in there, the hydrogens aren't going to add up appropriately.
Okay.
Somebody in the classroom, what do you think about the integration? Do we need to multiply anything, or the integration's good? Where are we at with integration? It's good. Why do you say that? They add up to 9. So we already said that this has, I'm still using this. Isn't this pin so fun? Universe pin. Let me get it off of that. People have told me they got to stop grading in red because they're like, students are offended by red. I'm like, well, you should see it, right? If I graded in this pen, that was like, you know, -5, you'd be like, well, I hate this space pen. It took points away from me. We said that there were 0 degrees of unsaturation here. And then Rachel just said that we don't need to multiply anything here because 6 + 1 + 2 does add up to 9. So what I would do if I were you, if I had this in front of me, and something I saw, I think Caleb did, which is super handy, is you can write these down. You can annotate this and say, I think I saw on your page over there, you had something that looked like this. You can draw a little cartoon of this, so you're kind of keeping yourself aligned here. I'll work on the actual spectrum that I'm using right now. The proton, or the signal at 1.05 is worth 6 protons. The signal at 1.97 here is worth 1 proton. Signal at 3.31 is worth 2 protons. Now, you got to start building with that. Start with a peak on the far right. What does that tell you? 2 methyl groups. Why do you say that, Lily? Just a good gut feeling. You are correct. The reason you're correct is because you can add to 6. 3 hydrogens and 3 hydrogens adds up to 6 hydrogens. So a way you can get to 6 H's over here is a CH3 and a CH3. How many neighbors do those CH3s have? 1. I'm assuming Lily correctly identified this as a doublet and said my CH3s better have 1 neighbor. So this whole chunk, all that, Lily got that entire piece from just this. Now we had to make some leaps mentally to get here, but this is why proton NMR is so useful. From this one signal that integrates to 6H, we drew all those atoms in. Yeah. It is 7 hydrogens because I'm accounting for the 6 hydrogens up here. And then this CH comes from the splitting pattern.
So
No, not the 1H. We're not there yet. My signal told me 6. Oh, geez. My signal told me 6 protons. Those are the 6 protons. I am saying that the 6 protons are next to a CH because they display as a doublet. And again, can we tell this is a doublet without the blow up? 2 peaks, twin towers, right? Any questions about how we got that one? I think this is the linchpin. Once you get this, the rest of the molecule is actually pretty easy. Yeah.
So when there's 6 hydrogen, that breaks up into like 3 hydrogen, 3 hydrogen,
Yeah.
and then you can tell by the neighbor groups that the CH, that's the neighbor.
Yeah, I put a CH here. So Rachel's question was, I put 2 CH3s because there was 6 hydrogens. Yes. And something that's different about this one compared to the others, this is 6 hydrogens, but notice this is 2 and 1. So the entire molecule doesn't have to be symmetric. It's just this piece that's symmetric. So I have two CH3s that are twins. I put my CH3s on a CH because this signal was a doublet. So I know that my 6 protons must neighbor only 1 proton. Well, that's this guy. How about this signal? What's it tell us? It doesn't necessarily have to be bound to a bromine, but it is closer to that bromine certainly than this signal is, right? Because I have moved it further to the left. So wherever the bromine is, I'm getting closer to it over here. I have a CH. And again, when you see something like this, if you don't have this signal in front of you up here, you just say, man, that CH has a lot of neighbors. There's a lot going on there. It's just a multiplet. Now you're going to find out that they gave you the correct number of splitting peaks here, but we're going to just say it's a CH with lots of neighbors present. Right, there's one piece. There's another piece. Gee whiz, that's a CH with a lot of neighbors. It seems like I kind of drew a CH with a bunch of neighbors over here too. What are the chances that this CH and that CH are the same CH? Pretty good. What's this signal tell me? A CH2. What's going on with its neighbors? It's what? It has only one neighbor, right? So my CH2 is going to be bound next to CH because it's a doublet, just like my 6H's were a doublet. I'm using a bunch of undefined bonds here. I don't know what else is over here or here, but they are not hydrogens because I can only have one neighbor next to that CH2. Here's my pieces. I got that chunk, and that chunk. Now I need to start assembling them in a way that makes sense for the proton NMR. A couple of you, and I'm sure some of you on Zoom are guilty of this as well. I just can't look over your shoulder. When I was walking around, I saw full molecules on your page without any other work. Do not do that. You will draw a wrong structure and you will spend your time trying to make that structure fit the spectrum. And it's just not going to happen. Eventually, you will become Jedi masters of NMR and you'll see an NMR and go, oh, molecule, got it. It's going to take you years to get there. So for now, build pieces and then assemble your puzzle pieces together. What's a key difference between our 6H over here and our 2H over here? Two H is pretty far to the left, yeah? What's pulling the 2H to the left? Bromine. So it probably makes sense that my CH2 here is near a bromine because it's the farthest de-shielded signal. So what I'm going to do is go out on a limb and say I've got a CH2 next to a bromine. Then I also have a carbon with a hydrogen next door over here because I know that from my piece. What am I missing? I've accounted for 1, 2 carbons, 1, 2, 3 hydrogens and a bromine. So I'm missing 2 additional carbons and 6 hydrogens. What are they? These guys, this isopropyl, 2 methyl groups. This is my proposed structure. Go away. Here we go. No. This is my proposed structure. First thing I want to do is make sure it adds up to the number of atoms that it should. 1, 2, 3, 4 carbons, 3, 6, 7, 8, 9 hydrogens, and a bromine. Check. This would be a good time to double check to make sure I don't break the octet rule. People go crazy when they do NMR and they start drawing weird things, or they're like, okay, I'll just put a couple more hydrogens there. Done. No Dr. Seuss carbons. This is someone who's gotten desperate in an NMR and they're just like drawing lines at that point. So make sure you don't break the octet rule anywhere. After you do that, then start trying to predict what the spectrum would look like. Gunnar. There is no double bond in this molecule because we got 0 degrees of unsaturation. Yeah. Correct. So there's no direct hydrogens attached there. Let me use some colors here. So the yellow are those guys. The yellow signals have one neighbor. It's there. The pink. Oh, that's way too close to red. The blue signal. It's a CH that has how many neighbors? Oh, way more than 3. 8. This carbon has a hydrogen and there's a house here, here, and here. So this house has 3, 6, 7, 8 neighbors, which means its peak is going to be split into 9 total peaks. And if you count up, I think these little ones over here, 1, 2, 3, 4, 5, 6, 7, 8, 9. You don't do that. You just say it's inundated. They live in a crowded neighborhood. They are surrounded by noisy people. Right? That's this signal. And in maybe green will show up well. That CH2 has no neighbors to the right, bless you, but only has one neighbor to the left. That's this signal. Make sense? If you had a CH2 attached to a methyl, that'd be like a CH3, CH2. Let's say we put a Br over here. This would show up as a quartet. That's right. That was like the previous one that I showed you as an example. You see it? Do we see why? Oh, 1? Yeah. You got to unmute yourself, 1. Sorry.
Isn't the green one has 2 neighbors?
The green one only has one neighbor. So there are 2 people that live in the greenhouse. They have one house next door because the bromine doesn't count, and one person lives in that house. So the greenhouse has one neighbor.
Why the bromine doesn't count?
Complicated physical reasons, but the splitting means that, well, there's no protons here, but splitting only occurs among carbons. So we only look at protons attached to carbons for reasons that I won't get into here. It's some scary dark physics. Carbons are houses. Everybody else is just I don't know, someone parked a big RV over here or something, or a boat. Hey, buddy. So we try another one. Does everybody see the task at hand here? Kind of how to approach this? Okay. Propose a structure for formula C4H7ClO. That is not carbon iodine, that's a Cl, so chlorine. Folks on Zoom, all my students in here are a little bit at a disadvantage that they're probably not looking at clear of a screen as you are. Can somebody on Zoom tell me what the splitting pattern is for this signal? How many peaks? You can use hand signals too. I think Emily is saying 2. This is a doublet. Oh, I'm still on green. How about that one? How many peaks there? Singlet. And the hardest one. So if you're in the room, that's maybe really hard to see, although I'm seeing a lot of squinting. Anybody here want to take a stab? What's the nature of that peak? That is a quartet. Very good. That's not how you spell quartet. I am surely rushing you, but it's 11:42, so I want to make sure we have enough time to talk through this. Are there any degrees of unsaturation in this molecule? There is 1 degree of unsaturation here. So my fake formula, I'm going to add the chlorine to the hydrogens. I'm going to ignore the oxygen. So my fake formula is C4H8. Adding the chlorine, ignoring the oxygen. A saturated molecule would have C4H what? Peyton. Saturated molecule C4H10. I'm missing 2 hydrogens from that molecule, so I have 1 degree of unsaturation. That is going to be a double bond or a ring. So that should help me as I'm trying to build this. Do I need to do anything with my integrations or am I good to go? Well, no. So I've already got done with my degrees of unsaturation. So I have 1 degree of unsaturation here. What I'm asking is, are my integrations here ready? Or do I need to multiply them? They're ready. 3 + 3 is 6, + 1 is 7. Those add up to 7. I only need 7. So 3 protons over here, 3 protons over here, 1 proton over here. With me so far? Now the hard work, figuring out the pieces. My 3 protons over here, I'm thinking are a CH3. How many neighbors does that CH3 have? 1. That piece exists somewhere in the molecule, CH3 with 1 neighbor next to it. How about over here? A CH3 with how many neighbors? 0. How do you get a CH3 to not have any neighbors in a carbon-based molecule? Yeah, like get the oxygen involved, right? So I know that I have a degree of unsaturation. A carbonyl acts as a beautiful spacer because it's really strange to have a carbon with no CH neighbors in there if it's part of a carbon chain. That means you have to have a carbon that has no hydrogens on it. What kind of carbon do we regularly work with that has no hydrogens on it? A carbonyl. Now this is challenging because I'm using carbon and oxygen in a double bond. I'm assuming a lot there, but I'm putting something in that's basically acting as a neighbor that can't have protons. I'll leave it as an X for now, but I'm going to use the carbonyl as my spacer to make this CH3 an island. to make sure that CH3 has no neighbors present, but is still part of the chain. Last thing over here is a CH with how many neighbors? 3. It's a quartet. Well, that is a CH next to a CH3. That's a CH next to a CH3. So those are probably related to each other. What else is likely bound to this signal? A chlorine. So let's use one of these bonds and say that I'm going to have a CH with a chlorine attached to it and a CH3. That Cl is going to pull this signal farther to the left and make it de-shielded. Now I need to worry about, so I've got this piece in there. I've got that piece in there. It's this guy I got to worry about. How can I bring my CH3 into this molecule? If I just draw a CH3 over here, I am missing some stuff, right? Not only is it going to complicate my splitting pattern here more, but I'm also going to be missing a carbon and an oxygen. So what I do is I put a carbonyl in here and then my CH3. I can't see anything in that circle. None of that shows up on my NMR because there's no protons present, but I assume they're there to make sense of the spectrum that I see. And that's why I think NMR is hard, because you're having to bring in pieces that you can't see. You're looking at shadows on a wall and you're assuming things about the world that's happening outside of you from very limited information. Anybody get that? I think this is the toughest one I've given you. Okay. Last thing I want to do, and I know I'm 2 minutes over, so I'm sorry, I'll move quick here. I want to show you one of my favorite sites that I wish I would have come up with. If you type into the Google machine or any search engine, NMR practice, CU Boulder. So the University of Colorado at Boulder came up with a beautiful way to practice NMR that I know right now you're not going to believe me because we're in a rush and the rest of this class is a little hectic at the end. But if you work at NMR long enough, a part of you, a very small part of you, deep in your soul is actually going to kind of enjoy this. And the reason I'm saying that is we like to solve puzzles. Humans are just designed to do that. Some of you do math for fun. That's called Sudoku, not my thing. Other of you do Wordle or crossword puzzles. We like solving puzzles, and an NMR is a puzzle. If you check out NMR practice CU Boulder, there are 20 different examples here of some NMR problems that you can work on. And I love the way they've laid this out because it's exactly how we've talked about it. I wish I would have come up with this, but I don't need to make a website because they've done it beautifully. What they do is they give you an unknown. So for problem 1, the unknown is C5H10O. They show you an IR spectrum. So it looks like, to me, it's got no CH bonds to sp2 hybridized carbons, but it does have CH bonds to sp3. It's got a carbonyl. And then they show you the proton NMR. And then they give you little boxes that you can click down here. So first thing you can do is you should always do your degrees of unsaturation. C5H10 has 1 degree of unsaturation. I can go check myself by going down here and clicking on this, and it'll show you how they calculated that. I made some assumptions about the IR, having a carbonyl present and no CH bonds. I can go down here and they'll show me the IR. Carbonyl, I don't think I would say a ketone yet, but I would say carbonyl present. Then you can go through and check just the structure. So you can draw it out, try and solve it. This is what it looks like. And if you need some more help beyond that, it'll show you the NMR answer with the molecule and the protons that are labeled and how they correspond to the spectra down here. It's awesome. I don't have a lot of, there's some okay homework problems here. If I'm trying to learn NMR and I'm you guys, I'd go to this website and just solve NMR after NMR after NMR until it clicks. And I promise you, if you do this enough, a light bulb will come on to where you just go, I got it. And not only is it going to be something that you can do, but it's something you'll take, like, I mean this not in a nerdy professor way, like you might actually take a little bit of pleasure in doing it. I apologize for running 5 minutes over and for the last couple of days being hectic. I know that we have dramatically increased the pace, but I appreciate you guys sticking with me. I have one more thing I need you to do tomorrow, and then you get to have like 3 weeks of summer before the fall semester starts. I will see you all tomorrow for the final. Remember, the final should really take up 2 hours if we're doing it right. So try and budget that. It's going to run beyond the normal class time. We will start at 10:30 and go until 12:30 if you need that much time. Good luck, and I'll see you in the morning.
You're saying, like, the website would be more helpful